Okay, let's start the chapter 2. In this chapter, I briefly introduce the history of ALD and then why we want to use the ALD for a lot of the application. So let me explain the scaling first. So basically, we are now using a lot of electronic gadget, like for example, smartphone or laptop, desktop, and then a lot of like IoT devices. Like for example, if you have like iPhone 10, and probably the most of the customer want to use like a faster iPhone, the larger capacity of in iPhone, and probably the high resolution of camera in the iPhone. And then also this is the Intel, the CPU, and probably in that those are in your all of the laptop or the desktop. And then like computer user also want to use like a fast computer, larger capacity in their hard disk drive, and then like better performance. So well, typically the chip is composed of a lot of like components, but most important component is the transistor. And then to increase the speed or capacity of the electronic gadget or the CPU or the chips, so we have to increase the number of the transistor. But as you know, as you can see, this the size of the iPhone, that the lateral size is very limited because the we have like limited size of the electronic gadget system, and then we have like limited like specific size of typical size of the laptop. So we have very limited area, and then to get the higher speed and larger capacity, we have to increase the transistor, but we have very limited the lateral size. That means we have to decrease the transistor size. So this is a really good example. So this is the almost the first transistor, and then we only put the one transistor of this size, but the number of the transistor is increased very fast, like a 16, 4500. It's now almost the 600 million. Well, probably at this time, so the number of the transistor is increased more than this. So, well, all of the transistor number of transistors is increase again. So we have to make the very tiny and tiny and tiny transistor again and again and again. So this is the another the driving force for the scaling. So this is the transistor shape, and then the transistor used to be like a two-dimensional shape, and then we have to decrease the size of transistor. Sometimes we can meet the requirements like performance requirements for the transistor. So to overcome that, the transistor structure is evolved from the two-dimensional to three-dimensional shape. It's now like almost a three-dimensional shape. Like for example, we have one planar, the channel area, but so from in the three-dimensional FinFET to transistor devices, we have uh, three-dimensional structure of the channel area, and then this channel area is covered with the three face around the metal gate, and then so that is evolved to the more like extreme case of the three-dimensional structure. So this is the transistor case, and then to increase the speed of our electronic gadget system, so we have to use smaller transistor, and then still to meet the performance, we have to make the three-dimensional the transistor devices. But in the memory device, for example, for your like a USB memory or the SSD in your laptop, so uh, we also have like device scaling in the memory devices. For example, so the flashy memory is very common, the memory device for all of the non-volatile memory. So the structure of the flash memory is very similar to the transistor, but it's a little bit different. But so we usually call that the device is a NAND structure, and typically there was used to be like a two-dimensional. That is like looks like the planar devices, but now they did change it to three-dimensional NAND structure. All of the companies now working on the new fabrication of the three-dimensional and the NAND structure. So basically, to meet the customer needs, we have to decrease the size. We have to increase the size of transistor, and we have to increase the number of transistor in the limited area. For that, we have to decrease the size of transistor, and then to meet the performance of the transistor, we have to change the structure of the transistor from the two-dimensional to three-dimensional. Very simple logic. So how we can make the very small things? So we call that method is microfabrication, and microfabrication is composed of the three different things, three different sub-components. So one is the deposition, and the second one is the photolithography, and then third one is etching. So the process is very simple. We just added some material, and we make some pattern on it, and then we remove some material area which is not used for the following the process. So this is the typical process to make the tiny transistor structure. So this is the movie made by Intel, and then, so I recommend you to take a look at this YouTube. Okay, so in the three-dimensional, three different the sub processes, we just keep focused on the coating, and then typically the sputtering and then chemical vapor deposition are used for the thin film coating, like adding material in the microfabrication process. Um, so that is really good for the two-dimensional structure. But so as you can see, this image I already explained in the previous page. We have to move from the two-dimensional to three-dimensional. So the film have to be coated even inside this very complicated the three-dimensional structure very uniformly. So, but if you use like sputtering and a chemical vapor deposition, it is really difficult and then very tricky. So due to like gas phase reaction and then the surface area difference, so we cannot make very conformal film. So to make the good device and then very well controlled device, we have to deposit very conformal film even inside the three-dimensional structure. So we need to have the another thing. So that is the answer is almost ALD, and then um, well, we already know we have to use the ALD for the conformal and like good thickness control the property. The ALD was invented from like almost 50 years ago in the Soviet Union. The basic concept was proposed in Soviet Union as the molecular layering, and then after almost the 10 years later in the Finland, so atomic layer epitaxy, the concept of atomic layer epitaxy was proposed by Tuomo Suntula. So the ALE, well, typically they used to be ALE, but now the ALE is referred to the other thing, atomic layer etching now. But so the original name of ALD was the ALE, atomic layer epitaxy. So that was developed for the electroluminescence devices. So the reason why Dr. Tuomo Suntula wanted to use that method for that is larger uniformity, and then that the ALE method can make the large batch process, and then they can easily control the ALE easily control the thickness of the layer. So this is the cross-section image of the multi-layer of the ALD deposited films. As you can see the sulfuric film inside the multi-layer structure. So this is the very easy the mechanism schematic drawing to explain the ALD mechanism. So we have a substrate, and then we just typically put this substrate into the vacuum, the chamber, and that is exposed to the precursor. And then precursor is adsorbed on the surface, and after formation of the one monolayer of the precursor, and then the other precursor cannot adsorb on the surface anymore because there is no available adsorption site. So after that, the molecule is pumped out, and then we expose the surface to the counter reactant. And then counter reactant reacted with this precursor, which is already observed on the surface. And then the counter reactant oxidized the precursor and then reduce the precursor and then purge out. So this is the precursor exposure, reactant exposure, precursor exposure purge, reactant exposure purge, and then precursor exposure. That is the one cycle is composed of the four steps. Because of that, the ALD film is only formed only on the surface through the surface reaction only. So we can make the excellent conformality, and then so we control the deposition of the ALD by controlling the number of the cycle. So the thickness is very easily controlled by controlling the number of ALD cycle. And then also, so once we wait for the full coverage of the precursor on the surface, so we can make very large uniformity. So the ALD film is very uniform even over like display devices that is larger than 3 meter by 3 meter substrate. That is the pretty large substrate. So this is the very typical the ALD movie of the titanium oxide. So we use the TiCl4 precursor and a water as a counter reactant. The surface, the TiCl4 absorb on that and then purge out, and then water comes in, and then water oxidize the TiCl4 to the TiO2. And then the surface is same, hydroxyl terminated, the TiCl4 comes in and react with the hydroxyl group and then making very strong bond on the surface through the chemical option, and then water also uh, react with one more time and then change the TiO2, and then we repeat this cycle, and then we can make very uniform film on the surface, very uniform film. This movie is made by the Banach, which is the the R&D ALD chamber making company in the Finland. Okay, so it sounds like very straightforward. Okay, let me compare the ALD with the very well-known the thin film deposition technique, the CVD. So what I assume that all of the student or the researcher is now watching the movie already have some knowledge or the background of the CVD. Typically, the CVD is the chemical vapor deposition, and it sounds like very similar to the ALD, but big different thing is like reaction time. So the CVD is the snowing. So the CVD process, the precursor reacts with the reactant or decompose uh, in the air, not air, like in the gas phase, and then that is form the nuclei or the cluster, and then they just formed on the film on the surface. Well, this is the gas phase reaction, but that is accompanied with the surface reaction at the same time, but dominant on the gas phase reaction. But in the ALD, that is the icing on the surface. It's very similar to the icing on the surface. So we have a lot of the precursor. Well, for example, this image, we have the water molecule. The water molecule comes in and then absorb on the surface, and then the water molecule is transformed to the ice. That is the only surface reaction. So in the ALD, so we only have the surface reaction, but not by the gas phase reaction. That is the really big difference from that of the CVD. So we only have the surface reaction. So this is the very important important growth mechanism of the ALD, because that gives a lot of the advantage like high excellent conformality and then some like surface dependent growth or something like that. So I already mentioned the ALD has really nice advantage, including the conformality. Like actually, the conformality, very good conformality is one of the top advantage of the ALD. So this is the very simple the diagram to show the difference of the conformality in the different technique. So if you have like a PVD, like for example the sputtering, so because all of the ion and radicals has a very high directionality, so we can coat it on only on the top surface which is exposed to the target. And then for the CVD, well, CVD still we can have the gas phase reaction, but that is the strongly depends on the flow dynamics. So we cannot make the very conformal film, but that is where we can coat it some film which is not directly exposed to the source of the CVD, but still we can make it, but that is not completed. So if you use the ALD, we can make really perfect the conformally coated film. But in the solution method, if you use like a Zolger method, you can make it, but you can see like a gap fill effect in like the structured area. So this is the advantage and disadvantage of ALD. PVD compared with the PVD and the CVD. The reaction is only surface reaction. The gross temperature is pretty low, like at room temperature to typical maximum temperature of the ALD is around 500 degrees C. Well, but typically around the 300 degrees C, that is the almost the maximum temperature because so uh, we have to keep preventing the thermal decomposition of the precursor. So the step coverage is excellent. The PVD CVD is not excellent, but impurity level is pretty good, but not better than the PVD. The thickness control the few angstrom cycle. Well, typically we can uh, theoretically we can control by the number of ALD cycles. So the gross per cycle, that is the minimum unit to control the thickness level. So the GPC is around like angstrom per cycle level, so we can control the angstrom thickness level. And then the wafer uniformity is good. But main disadvantage of the ALD is a very slow growth rate. So well, you may expect that. So we grow the layer by layer to make the thin film. So definitely that is the slower, much slower than the PVD and then CVD. Like the snowing, that is so fast, but the icing on the surface, that is not very fast. So the temperature area is the temperature and the pressure area is looks like that. The temperature is around the 300 degrees C, that is lower than the CVD. The step coverage is pretty good compared to the CVD and PVD. So I really like this slide. So where the growth rate of the ALD used to be very slow and that is not good for the high volume manufacturing. But now the condition was changed. So not too thin and slow anymore. So this is the very impressive the graph from the U.S. title, the production, and then the crude oil price. So as you know, like few years ago, the oil price was very high, but at some point, the oil price is to drop down, and then that oil price is not increase again. So the main reason behind that is like the USA, the oil making company, they already have some technology to get the shale gas, that is the gas production, the technology from the rocks and then sands. But the fabrication cost for that was very high, but oil price is high enough. So that was the time to develop, that was the time to use the expensive technology because there the price has very the compatible with the crude oil prices. So that's the situation is quite same in the ALD system. So we continuously decreasing down the device size, and then we change the structure of the device from the two-dimensional to three-dimensional. So for example, like 10 years ago, we had to deposit like 100 nanometer film thickness. So for example, if you have like 1 angstrom per cycle ALD process, we have to do 10 cycle. For example, one cycle takes like 10 seconds. Total time is almost a 10,000 second. that is a 2 hour and then 40 minutes to deposit 100 nanometer thin film. So we have to spend almost a 2.5 hours. So that is not uh, usable in the high volume manufacturing. Probably it's good for the like lab scale, but not for the commercial scale. But now we just deposit 1 nanometer, so the thickness is very thin, thin enough. And then with the same condition, we only have 100 seconds. That is the 1 minute and then 30 second, 1.5 minutes. That is a quite the acceptable in the high volume manufacturing. So that means we can use the ALD for the various applications, well, typically in the semiconductor device fabrication, because the thickness range is quite thin enough for the ALD process. So the ALD reaction step is composed of 4 different steps. First of all, that is the precursor exposure step. Second is the purge step. And then third one is the counter-reactant step. Fourth one, the purge step. In the first step, so the precursor molecule jump on the surface through surface self-saturated reaction mechanism. So I will explain in the later. And then we remove the excessive molecule by pumping down. And then we also expose the counter-reactant to the surface, and then the counter-reactant react with the precursor, and then that is changed to the surface to oxide or the pure metal, and pump down the excessive the counter-reactant or the byproduct. So let's take a look at what is the precursor and the counter-reactant. The precursor, that is the chemical, is composed of the elements that we really want to deposit, uh, and the ligand, that gives the physical and chemical property to the precursor itself. So, for example, this is some 4 different the precursor molecular structures. This is the lithium alkyl cyclopentadienyl. So if you want to deposit the lithium metal, you have to use this precursor. But as you expect that, so we have to cut down in this bonding, and then we have to remove these the carbon and hydrogen things. So we call this is the ligand, and then ligands give physical, like for example, like vapor pressure, and then chemical, the property to the precursor. For example, if you change the ligand, you can change the vapor pressure, and then also you can change the chemical reactivity. So this is a cobalt precursor, titanium precursor, aluminum precursor. The counter-reactant means the chemical for the oxidation or the reduction of the precursor to form the desired material. Like your surface is exposed to the precursor first, and then the precursor of the surface, and then next your surface is exposed to the counter-reactant. Like for example, hydrogen reduce this the lithium precursor, and then remove this the ligand, and then leave the metal only. Like for also sometimes if you use like water, oxygen and ozone, you oxidize the TiCl for the precursor, and then leaves the TiO2, like titanium the oxide on the surface as a film, the foam. So this is the precursor and a counter-reactant, like some part of the material used for